Now I have another challenge for you. Think about a hypothetical 2-qubit gate which has this effect. You can regard it as a quantum copying machine. You have 2 qubits coming in and 2 qubits coming out. Of course, that's necessarily so. You must have the same number of qubits going in and coming out because you don't lose qubits along the way. And the desired feature of this gate is that it copies the state of the first qubit. So if the first qubit is in the state psi, and psi can be any state, and the lower qubit is some fixed reference state S. You can choose it in a suitable way, but it doesn't, you fix it once and for all. So it's some state S that is fixed, and the upper state is psi, and the psi is arbitrary. You can change that. And what you want the gate to do is that the 2 output qubits are then both in the state psi. So effectively, you've copied the state of the upper qubit. Do you think that such a gate exists? In a way, I've warned you. I've warned you several times today that copying of qubits is a problem. And so the question was a bit rhetorical.
Yes. So it doesn't exist the way you ask it implied. But secondly, it doesn't look like a Unitarian transformation.
Yeah, I mean, in fact, there's no unitary transformation which does that for you. Yeah. And let me show you a quick proof why this is impossible. We have this wondrous machine which does the copying for us. Yeah. What would that imply if such a machine existed? And mathematically, this would mean that a unitary operator applied to the product state psi tensor S gives psi tensor psi. If instead of psi we input another state phi, then of course this should also work. Yeah, the copier should also work. So we should also have u phi tensor S that should give phi tensor phi. Yeah. And that should work for arbitrary states psi and phi. Now we can take the scalar product of these 2 equations. So we can take the scalar product of the 2 left-hand sides and the scalar product of the 2 right-hand sides. The scalar product of the 2 left-hand sides, that's psi phi times S. And this should be equal to the scalar product of the 2 right-hand sides. And that is psi phi times psi phi. This auxiliary state, S, that's a normalized state. So this is equal to 1. And on the right-hand side, this is psi phi scalar product squared. Yeah, not absolute value squared, but squared. So we have the condition for this to hold, that the scalar product of psi and phi squared must be equal to the scalar product of psi and phi. Now, the only two numbers which are their own square are 0 and 1. Yeah? So this can only be satisfied if the scalar product of psi with phi is either 0 or 1. This means that the condition for copying can actually be satisfied, but only if the two states psi and phi are either identical, then their scalar product is 1, or they are orthogonal, in which case their scalar product is 0. But as soon as the two states are neither identical nor orthogonal, it doesn't work. So while such a copier or such a unitary transformation that does the copying may actually exist for special input states psi, it doesn't exist for arbitrary psi. Yeah? So we can, for example, we can construct a 2-qubit gate which copies standard basis states. That exists. But then such a copier will not be able to copy arbitrary superposition states, which is what we would like to have. Yeah? So this doesn't work for arbitrary psis. And this impossibility is known as the no-cloning theorem. And that's a very basic, very fundamental result in quantum information. And you should remember this little proof that I showed you. To conclude today's lecture, I want to show you one single 3-qubit gate. I said that a quantum computer can be built entirely from single qubit and 2-qubit gates, but I want to show you nevertheless one example of a 3-qubit gate, and that's the so-called Toffoli gate. It's an example of a multiply controlled knot in the sense that there are two control qubits and something happens to the target only if both control qubits are in the basis state 1. You see graphically, it's represented by a symbol which is very similar to the controlled knot, only that you have on top another control qubit. So here's the action on basis states. Yeah, so C1, C2 are the two control qubits, and they are in the basis state 0 or 1, and the target at the bottom is also 0 or 1. The two control qubits are unchanged, and the target qubit is flips. So you add 1 mod 2, which is the flip, if and only if both control qubits are equal to 1, are in the basis state 1. I show you the matrix representation of the Toffoli gate. Now this acts in the 3-qubit Hilbert space. The 3-qubit Hilbert space has dimension 2 to the power 3, which is 8. So it's an 8 by 8 matrix. And it has the entries. It's again, here it's shown as a 4 by 4 matrix where each entry is in itself a 2 by 2 matrix. And the zeros are not shown, they are just empty. And so it's on the diagonal, it's all 2 by 2 unit matrices. Only in the bottom right you have the Pauli X, which represents the knot, the flip. This is a unitary matrix, and therefore this is confirmation that a unitary transformation exists, which has precisely the effect that I showed you. Now, without proof, But this is one of the problems on your problem set. And I hope that more of you will work on that for next week. So please show in your homework that the Toffoli gate can be built from single and 2-qubit gates in the manner that I showed you here on the right-hand side. It's not so trivial. It's one of the shortest representations of the Toffoli gate in terms of single and 2-qubit gates. So you have, in terms of 2-qubit gates, you have only CNOTs. Yeah, so if you have many CNOTs, and in between you have single qubit gates. So these are Hadamars, and the T's are the pi 8 gates, and the T dagger are the inverse of a T gate. Yeah? So that's something for you to show at home, and you can either do it by example, so you can just try out various combinations of basis states and then see what happens as you go through the circuit on the right-hand side, or you can prove it using the matrices, the respective matrices that represent the gates on the right-hand side. One reason I wanted to show you the Toffoli gate is that it's a specific example where a 3-qubit, so a unitary transformation involving more than 2 qubits can be broken down into a sequence of unitary transformations each involving just 1 or 2 qubits. Yeah, and it's a special case of this more general statement that any unitary transformation on n qubits can be broken down into transformations of 1 or 2 qubits at a time. So this leads me to the final slide of today's lecture about the universal set for a quantum computer. The statement is that an arbitrary quantum circuit, meaning an arbitrary unitary transformation on n qubits for an arbitrary number of qubits, can always be broken down into single qubit operations, which last week, and so unitary transformations on a single qubit, which last week we visualized as rotations on the Bloch sphere, plus 2-qubit transformations, and you can actually you can sharpen the result. It's actually sufficient to use CNOTs. It's the only 2-qubit gate that you need. That's why it's so important and so fundamental. Yeah. So you can build everything from just single qubit and CNOT. And then to complete the picture, yeah, in the sort of at the end of your unitary transformation, to read out classical results, you have measurements. So this is the third component. And from these 3 components, you can build any quantum circuit, any quantum algorithm affected by this quantum circuit. And then there's one further, and this is an exact result. And then there's one further result that I alluded to earlier, that in terms of the single qubit operations, you can also restrict it further to just a very small set of gate types. Strictly speaking, just 2, namely the Hadamard gate and the T gate, the pi 8 gate. These 2 gates are sufficient. This is the statement of a theorem called the Solovay-Kitaev theorem. And this is an approximate result in the sense that you can prescribe any error, you can make the error as small as you like, but not exactly equal to 0. And within this error bound, you can effect any single qubit operation by combinations of just these two gates, H and T. Yeah? So in this sense, the universal set of quantum computation consists of three gates: the Hadamard gate, the T gate, and the C0 gate. And from this, you can build everything.